Well, you can see from the title of my talk, it concerns universality and statistical mechanics. And I hope to tell you something about what the interesting problems in statistical mechanics are, at least for me, and the notion of universality, which is a very intriguing one, and for which we have some partial understanding, I would say. In high dimension, I think we understand things rather well. In two dimensions, we should understand things better, and we have some partial results there. Where we really would like to have good results is in three dimensions. That's the physical world of statistical mechanics. Unfortunately, there, the results are rather sparse. So to describe universality, I first have to give you a sense for what a phase transition is, because universality really concerns phase transitions. Okay, so I will begin very generally with the notion, with the example of a system of spins, which you can imagine to be plus or minus 1 on a lattice. You can imagine the lattice to be two-dimensional or any dimension, but above 2 is better for these purposes. And imagine these little spins to be like a magnet, and they interact. What happens is at high temperature, these spins, if you take a bar of magnet and you heat it up, the spins become all disordered, and you have no net magnetization in your system. It doesn't really act like a magnet. So at high temperature, these spins are disordered. They're unaligned. And if I look at spin-spin correlation, in other words, what the spin at the origin does, how it interacts with a spin far away, you have an exponential decay at high temperature. In other words, the spin at the origin is more or less independent of the spin far away. However, there's some residual exponential decay, and this length here, LT, is called the correlation length. That's the length at which they're approximately oriented together.
What is the order of LT in terms of spacing between the
I have a unit spacing here.
No, but L of T, what is the order of L of T? How big it is?
Well, I'll explain. That's really the crucial thing. How does L of T grow and so forth as you change temperature? L of T will be very large. L of T will be very small when temperature is high.
What's that small?
Like one. Like one. Mm-hmm. And when the temperature goes to the critical temperature, this L of T is going to go to infinity. So the length is going to get very, very large. Now, at low temperature, these spins are basically ordered. In other words, they all tend to line up, as it does in a magnet. And you get a magnetization, which I've indicated here. So the spin here and the spin here, they may be both up or both down, but they're aligned. So the spin, this is approximately 1. Not only is it positive, it's approximately 1. And the spins are ordered. Now, I'll define these expectations more carefully in a minute, but at the moment, I just want to give the general picture.
If you have it divided into pieces, one be plus, one another minus, one will be as big as everything, and there will be no global magnetization.
That's right, but that's not the way things work generally. I mean, you can have such a thing if you change boundary conditions, but I'm not going to get into that. You can have phase separation and things like that. So this is the magnetization. Now the transition temperature is a temperature in between high and low temperature. It's generally speaking, not always, it's a unique temperature, believed to be a unique temperature, and it's called a critical temperature. And at this point, the magnetization vanishes. That's the nature of a second order transition. The magnetization should vanish, and the correlation length should be infinite. So the spins don't completely order, but they don't decay exponentially either. And it's at this special temperature, which is, you can think of, if you're thinking of a physical system, as a liquid-gas transition. Liquid being the ordered, the gas being the disordered transition. And what we want to understand is what happens in the neighborhood of this critical temperature. The qualitative nature of these spins or gases or whatever you have is remarkably independent of the details of how these systems interact. That is universality. So let me put this on the board, on the screen.
So in the low temperature mode, there's no dependence on distance at all? Or?
Well, there is, but it's very, well, it depends on how you have it set up. But roughly speaking, the spins are mostly aligned, and it gets, when they're very close, they tend to be lined up, maybe not so much, but farther away. When they're very close, they're even more lined up, but farther away, the point is that they still remain aligned at long distances, so that macroscopically, they're all more or less pointing in the same direction. You can have little islands where they turn around, but this is, at very low temperatures, this is nearly 1, which is the maximum this thing can take, basically. So now here's the universality hypothesis. This is explained in a very general way. We'll get more concrete in a moment. First of all, there's a singularity. Well, you can see a singularity here. If I write it this way, the length has become infinite, and the magnetization below Tc is 0, so this magnetization goes up and it has a singularity at Tc. But the singularity at Tc and the scaling limit, in other words, the long-distance behavior of spin-spin correlation, not just spin-spin, but multi-spin correlations. If you look at the asymptotic long-distance behavior, all these things are supposed to be independent of the details of the model.
What is the constant in this? What order of the constant?
What's this new here?
No, this M of T is equivalent to this, but also there's a constant there, constant in
Sorry, which are you referring?
Constant in front of T minus.
There's a constant here. This constant's, let's call it of order unity. Yes, it varies. It can vary from system to system. There is a prefactor here which is very system dependent. So I didn't put that in. Perhaps I should have. There's a prefactor which is not universal. Okay, it's not 0, but it is not universal. But what the point is that the way this length, for example, which I've tried to explain here, the way this diverges, the rate at which it diverges, this is supposed to be universal. In other words, it really doesn't much matter what the details of the system are. And these things were first observed, I would say, I imagine they were first observed in physics, where one did experiments to measure things like specific heat and so forth. And people noticed that although this temperature is model dependent, this Tc is by no means universal. It varies from one system to another. But the divergence, this length here, at the way it diverges at this temperature, that's universal. You have a question, or?
There is a pointer.
Pointer, okay. Maybe that's better. I'm not used to these, but yeah, okay. So now, when I say universality, I should really make a couple of points here. It's independent, as I say, of the details of the model, but it does depend upon a number of things which are important and one cannot neglect. And this is only a partial list of things it does depend upon. So when I say it doesn't depend upon details, there are certain things it does depend upon. First of all, and probably most importantly, the dimension of the space. If I have a magnet or if I have a liquid film, or a full three-dimensional liquid, or if I imagine I could do experiments in higher dimensions, then the dimension of the space will change the singularities that one sees. It will change the long-distance behavior. So dimensional space is of primary importance, as we'll see. Symmetry of the system is extremely important. Generally speaking, when I'm talking about these spin systems here, these have a symmetry, which is a Z2 symmetry. If you flip all spins up and you make them all down, the energy remains the same. So that's a Z2. Some symmetries, if you look at superconductivity, there's a U1 or O2 symmetry. Sometimes you have an SU2 higher symmetries. There are ZP symmetries. These symmetries also are extremely important and generally speaking, affect these exponents and the long-distance behavior. The interaction should be short range. In other words, the interaction which couples the system and at the Hamiltonian level shouldn't be too long range. Short range is perhaps too strong a word. You can't have very long distance behavior. That's not to say that something like a Coulomb can't be treated, but Coulomb and a short range interaction will give you different physics. Finally, something which is sometimes forgotten is that your interaction, the things that you look at, the laws of physics should be translation invariant. So if I look at a sample here and here, the interaction should not change. So let me begin by giving you the simplest, perhaps artificial example of universality and critical phenomena. And it's a funny way of writing the central limit theorem, but I will explain it in this context because you might find it useful. So imagine that we have a random walk on a d-dimensional lattice, and the walk starts at 0. Now, if I talk about random walks, there's generally speaking no notion of temperature. I'm going to introduce a fake temperature. It's as part of a generating function here. And in the generating function, I call it gt of x. I just sum over t to the minus n the probability that the walk at the nth step has the value x, where x is also in CD. Okay? Now, it's easy to see that since probability can't be bigger than 1, this converges for t bigger than tc. Okay? Tc equals 1 is, in this case, my critical temperature. I mean, there's no real critical temperature here, but for the purposes of exposition, this is quite useful. There is a singularity at Tc in this sum, generally speaking. So let's see what happens. This sum can be explicitly done, and it is basically the Green's function of minus Laplacian with some coefficient, depending upon the details of how the random walk is set up, plus t minus Tc. Well, Tc here is 1. So if the temperature is above 1, you need it to make the thing converge. We just have a Green's function of a Laplacian with a mass. I think of this as being the mass. And if you're at Tc, this difference is 0, and the Green's function decays like x to the minus d over 2. And that's more or less independent of the details of how the walk is set up. That's at Tc. Now, for t not equal to cTc, this thing decays exponentially fast because of this killing factor. And it decays with a length which is t minus Tc to the minus a half power. So the length is divergent, as it should be, with this nu equal to a half here. And the scaling limit for, of course, random walks in great generality, the steps of the walk don't have to be independent, but you have to have some asymptotic independence. And then the scaling limit here is going to be Brownian motion, which has all kinds of additional symmetries that is not present in the original random walk. So this is perhaps the simplest example of universality. The central limit theorem is a very simple and useful example of universality.
Is the capital D the Green's function, little d?
This d here,
In the Green's function, yeah.
that's like a diffusion constant.
So how do things depend on the
They don't really depend upon dimension except right here.
So you assume some distribution of probabilities.
Yes, and the details of the probability distribution I'm not going to get into. And the point is, they may affect this constant d, but they will not, and they may affect this constant c, but they will not affect this d minus 2. And they will not affect this power half. Again, as a prefactor, which I've omitted, it will definitely affect this. Okay? So the singularities and the long-distance behavior are what's universal here, as long as it's a random walk in any reasonable sense of the word. Now, let me turn to the Ising model. Maybe I'll come back to this, because I don't think I need this right now. Maybe I'll come back to that later. So the Ising model, where I want to make this spin, this is the classic example of of a model in statistical mechanics. And it's a more precise version of what I was telling you at the start of the talk. We have spins which take values plus and minus 1. They're labeled by points in the lattice, and I stick to a big box so I can make sense of some of my sums. And I define an interaction or an energy for a spin configuration. You look at any spin configuration and you give it an energy. First, imagine this epsilon here is 0. We'll add perturbations later to show that things don't matter. The epsilon isn't important. But for the moment, imagine epsilon to be 0. And what all this does is it favors, you can see your Hamiltonian is smallest, your energy is lowest, when all the spins are aligned. They are all either all plus or all minus. I have summed here over what are called nearest neighbor lattice sites, so they should be adjacent lattice sites. And if your spins are not aligned, then your energy increases. Okay, so if the spins are sort of random, then this energy gets very large. And when I exponentiate it here, that's highly suppressed. So let me come back. So this F is, let's say, a perturbation where you don't have nearest neighbors. It could have 4 spin interactions. It should be short range. And this is what I mean by short range. The decay is a function of J minus K. That's the translation invariance, which I have to insist upon. And then the K of R decays, let's say, exponentially fast. I could put any prefactor here I wanted to, as long as I have some kind of exponential decay. Exponential decay isn't even necessary. You need some fast power law. If your power law is too slow, then universality will fail. So the power law, just imagine it's exponential for simplicity. And then we form what's called the partition function, which is a generating function, if you like. You look at the energy of the spin configuration, you exponentiate it. This is the Gibbs weight, and you divide by the temperature. Divide by the temperature. So see, if the temperature is let's say, is very low, that means that this is a small number. That means that the effects of the Hamiltonian are at low temperature. You want to minimize the energy. Otherwise, you get a very small contribution. And when you minimize the energy, all the spins want to point in the same direction. And therefore, the sigma j's are all ordered. They're either all up or basically all down in the limit that the temperature goes to 0. And at positive temperature, there are just fluctuations around that. And again, if the temperature is high, that means T is very large. Then the effect of this Hamiltonian is negligible. If this T is large, you're dividing by a large number. And then the spins are basically just take values plus and minus 1. So you get a random sequence of numbers and so these spins, the spin at 0 and the spin at x don't know about each other, and they decay basically exponentially fast. And of course, it's at the intermediate temperature where the transition takes place. Now, there's a famous solution to this problem that was given by Lars Ansager come over here, by Lars Ansager in the 40s. And what he was able to do, among other things, was to compute the partition function. So here epsilon should be 0, as I said, so this would just be nearest neighbors. Epsilon should be 0. And then basically he showed this whole Ising spin system, this whole sum and partition function, could all be computed explicitly. Explicit computations. And I'll explain a little bit about the mathematics behind that later if I have a chance. So now, and then he showed there was a phase transition, and he computed everything about it, basically. I mean, there's nothing, there are some details which are actually still open, but basically he completely solved the model in 2 dimensions, and it was a real tour de force. So, to explain the phase transition here, let me do something else, which is to compute what's called the free energy, which means I take the partition function, in other words, this generating function here. You sum over all the spin configurations weighted, divided by temperature. And then you take the log, because the thing grows, as the volume gets big, this thing grows exponentially, so you should take the log and divide by the volume, and take the limit as the volume goes to the to Z2. And this is the thermodynamic limit, and this limit exists under great generality. It's not, this is called a free energy, and it depends upon epsilon. As I say, he computed the case of epsilon equals 0. Now, here's what Onsager discovered, that for epsilon equals 0, this f of t is analytic as a function of temperature. The variation in temperature is completely smooth, except when t is equal to Tc, which can depend upon epsilon. But he only treated the case epsilon 0. And at t equals Tc, there's a singularity. The singularity is captured, can be seen in the second derivative. And the second derivative has a log divergence. Okay? And the spin-spin correlation has a divergence. He also calculated that. The length is t minus Tc to the minus 1. And if you remember, for random walk, we found it was minus a half. So this is a little different. And what Haru Pinson and I have recently done is to show that all of Onsager's results, not surprisingly, go through when I have a small perturbation of almost any kind, as long as it's reasonably local and even. Something like this would be fine. And so this is, but the temperature changes. Okay? These constants change. We can't compute these constants, but we know that the singularities, and there's a prefactor here which changes, but this singularity, this 1, this log, are unchanged. So the singularity is the same. We need to require, unfortunately, that this epsilon is small. I mean,
this is for a numerical result.
No. This is a rigorous result.
For a rigorous result.
It's a rigorous. See, so there's an exact solution for epsilon equals 0. That's Onsager.
I mean for k, for arbitrary k.
Yeah, for arbitrary k, we can do this provided the epsilon is small and the k has some exponential decay. So there's a rigorous result that says that even though we can't solve the model exactly, it's no longer integrable for epsilon positive, it's still, the integrability captures all the singularities that Onsager saw, and there's no difference. And the fact that these singularities don't change is universality. It's a form of universality.
Okay, the critical temperature depends only on epsilon and not on k.
Oh, it does. It depends upon epsilon, and it depends upon k, and it depends upon a host of things. Absolutely. It depends upon k. It depends upon all the details of f. But I've only indicated the fact that it has an epsilon dependence, so I don't have to keep too many other indices. Yes, Lisa.
With power law, is it experimentally verifiable? Is it an experiment?
Yeah, well, this is 2 dimensions, so you have to look at certain films. I imagine it can be done. I wouldn't want to say for sure. I know that it has been done for spins which take continuous values, and then this is all a bit different. So you have an O2 symmetry, and they've done experiments on liquid helium films, and then they agree very, very well.
I mean the Heisenberg model.
No, this is O2 model, O2. So it's like a superfluid film.
Do you have universality in that case?
Yes. Yes. Well, at the what's called Cosmos-Thales edge is universality. But let me not get into that. So let me stick with a simple case here. And so, as I say, what's universal are these how the lengths diverge, how the asymptotic behavior of spin-spin correlations, and so forth. Now, let's see, there's more to put up here. But let me go to high dimension now. I've talked about 2 dimensions, and I said we understand high dimension reasonably well. So let me tell you what we understand about high dimension. So high dimension means bigger than 5. Actually, 4 can also be done, but things are a little bit different. And here you get the t minus Tc to the half power, just as you did in random walk. The spin-spin correlation behaves like x over d minus 2, the fundamental solution of the Green's function. So that's just like random walk as well.
This is also for epsilon 0.
This is for any, this is epsilon positive. it can be done for epsilon positive. It's very general here. Epsilon doesn't have to even be small in the case. So, well, no, actually, let me not be too precise about the values of epsilon. But there's a whole range. There's a very wide range of epsilons for which one knows all these things. The multi-spin correlations that I've written here, a 4-spin correlation, the x's are, let's say, all far apart from each other. They factor into products of pairs. That's the Gaussian nature, that higher endpoint correlations factor into just pair correlations. So the problem is very, very simple. And here you have a couple of extra permutations. Now the spin-spin correlation, which I didn't tell you about in the Ising model, has also been computed, and I just mentioned it back here. You see, instead of being d minus 2, it's just x to the quarter. This was computed by Onsager when epsilon equals 0. We have not yet, but I think it's only a matter of time before somebody proves that this quarter also doesn't change with epsilon.
Yes, again, d equals 2.
This is back. I'll come back to here for d equals 2. Just to compare the quarter here with a d minus 2 over here. This is for d bigger than 5. This black stuff is for d. So you see, if you substitute d equals 2 here, you won't get the right answer. This is a quarter. Okay, so this is only valid for d bigger than or equal to 5. Actually, 4 also works. But in 4 dimensions, there is a correction to here, which is kind of interesting, which is a log t minus tc to the 1/4 power, or 1/3 power, or 1/6, I forget. There's a fractional power of a log which appears here in 4 dimensions. So it's not quite the same as the 5. There are logarithmic corrections, and this is I think one of the impressive achievements of renormalization group. These are all done by renormalization group methods. For epsilon equals 0, there's no renormalization group. It's exact solution, but for epsilon not equal to 0, we use renormalization group methods. Many of these fine details you need renormalization group methods for as well.
You say for G, large G, you have exact solution also?
No, you don't have an exact solution, but you know everything about the system.
It's related to the fact that the self-avoiding walk.
Yes, that's a good point. It's related to the fact that if I have self-avoiding walks, or if I have Brownian paths in d bigger than 4 dimensions don't cross. And so there's really very little interaction in the system in high dimensions. So systems in high dimensions are not so exciting. At least in this kinds of spin systems.
Can you extend these non-existence proofs in Blackboard field theory to the equal 4 case?
Well, it's very much connected. The methods that are used here are very much connected to field theory. That's certainly true. And in fact, let me just comment that the results that Pinson and I have for epsilon small really are almost, well, they're a simpler version of field theoretic methods that were used by Gavensky and Kupianen, for example, to understand field theories like Gros-Neveu in 2 dimensions. So although the models are completely different, the methods are very, very closely related to field theoretic ones. But this is a simpler example, I would say. I mean, our techniques are a little bit simpler than they are in the field theoretic context for Gros-Neveu, for example. Now, I want to go to a continuum model just to change speed a little bit. And since this is also a section in PDE, let me put this up. Now I guess it's my turn to come over here. And talk about coupled anharmonic oscillators. Yeah, I guess that's visible. So this sounds like a completely different topic, but in fact it's the same, disguised. I have a bunch of, these are just derivatives. This is a Laplacian, and I'm taking n harmonic oscillators, and here they're anharmonic actually, because I have a 4th power, x to the 4th. It has 2 wells. It has xj equals b, xj equals minus b. That minimizes this, so there are 2 wells. So it's a double well anharmonic oscillator, and they're not independent because they're coupled by nearest neighbors. Okay. Now notice when lambda gets very near 1, lambda gets big, xj is plus or minus b approximately. Xj is plus or minus b, you should think of that as like plus or minus spin system. Now, what is the analog of free energy? Well, I take the lowest eigenvalue of this differential operator, which depends upon n, so I've indicated here. 0 means it's the lowest eigenvalue, and it depends upon this parameter b. And we take the limit as n goes to infinity. Now, this eigenvalue depends upon n in a linear way, so we divide by n, take the limit as n goes to infinity. And then the statement is, this is a chain, so the statement is that for lambda very large, this lambda right here, very big, there exists a beta critical. The second derivative of this has a log singularity, just as it had in the Ising. The energy gap is beta minus beta critical. That's like this minus 1 that we saw in the correlation length divergence. So there's a 1 here. The first power, I haven't put it in, but that 1 is like the 1 in the correlation length divergence. Now, if you do the same thing in higher dimensions, in other words, this index I lies on the lattice of dimension bigger than 4, then you get b minus b critical to the half. So this is very closely related to the Ising model.
What are EN0 and EN2?
Yes, sorry. E0n is the lowest energy eigenstate for this. Okay. It's not. It's a linear problem. It's a linear problem with a double well. Okay. So it's a set of coupled anharmonic oscillators. It has a ground state, and the 2 here, that represents the second excited state, not the first, the second excited state. And the difference between the first and the second excited state behaves like b minus b critical for b near b critical. So, for example, if b is not equal to b critical, there's a gap between the lowest and the second eigenstate. But as b equals b critical and n goes to infinity, I should have had a limit here, n goes to infinity, this gap, this difference between the lowest eigenstate and its second excited state goes to 0 at beta critical. Okay.
So the low state is absolutely absolutely symmetric state.
Yes, that's right. And then there's a second excited state.
They are
Yes.
symmetric.
Right. I should have a limit here, n goes to infinity. In other words, I have to take the limit that n gets very large for this result to hold. Because if I don't, then there's always a gap between the first and second excited states, because it's a compact operator, so it has a compact resolvent, rather. So this is in the limit that n gets large that you get this singularity. In other words, the energy levels come closer and closer together if my b is close to beta critical. So these are very closely related to Ising.
Scaling limit?
Hmm?
There is scaling limit?
There is a scaling limit for this, and the scaling limit is the phi to the 4th field theory. It's really the same. So we can show this. I mean, one of the problems is we can prove all this if lambda is large. It should be true when lambda is even small. Okay? All this stuff should hold for lambda small, but our methods are perturbative, and so we can't treat that case yet.
Sorry.
Yes.
0 and the first are the same, yes?
The 0th is the lowest eigenstate. It's also the first eigenstate. Sorry, I'm sorry. That's maybe physics notation. It's the lowest eigenstate, and this is the second, the lowest eigenstate.
Yes, and the next corresponds to 1 kink, yeah?
The 1 corresponds to 1 kink and 2 kinks and so forth. Yes, I think that's probably correct.
And if lambda is equal to 0, what happens in this case?
If lambda equals 0, then you get this kind of behavior, half. I mean, if you had it's different. The minute lambda is positive, everything changes. Everything changes the minute lambda is positive. And if you have lambda equals 0, the problem's soluble. It's a bunch of harmonic oscillators, and then typically you get this square root behavior, it's central limit type behavior.
Do you study especially the case of lambda tends to infinity when the connection?
Yeah, we do. We like to do that because it's easier to make the connection with Ising. It's much easier to make the connection with Ising. Because when lambda is large, you see, x wants to be near plus or minus b. Otherwise, it pays a penalty in the... Now, I should say, to do this, this is a problem in differential operators, if you like. However, we do not analyze a differential operator directly. We analyze it through Feynman-Katz. So you really need functional integral approach to treat these things. You cannot, I mean, we cannot, and I don't think anybody's been very successful at treating this thing, especially in the limit of large n, directly at the PDE level. You need the path integrals to control the low energy behavior, especially near the critical temperature. It's essential. Now, let me give you some idea about what's special about 2 dimensions. And this transparency may not mean a lot to some people, but in 2 dimensions, there's something quite remarkable that happens that was essentially discovered by Onsager, but certainly not stated in this language. And the statement is, just imagine this epsilon is equal to 0 for the moment, is that the partition function can be written as what I call a Grassmann integral of something which is quadratic. You have this phi here as a field and another field here, which I'll explain in a second. And we're integrating over the fields. Now, if these fields were real numbers, which they are not, this would be a Gaussian integral. Okay? These, however, are Grassmann integrals, and the fields, which you see down here, actually are anti-commuting.
Is this the Ising model way?
Ising model, yes, sorry. This is Ising model. This is the partition function for the Ising model. And at energy at epsilon equals 0, when I just have the nearest neighbor case, it is exactly representable as a kind of Gaussian integral with a matrix up here, which is really a Dirac operator. And you see that at t equals tc, this matrix element vanishes. And therefore, the inverse of this has a singularity. It's a fundamental solution to the Dirac operator, and you get power laws and so forth that come out of that.
It's a continuous model.
This is a discrete model. Actually, this is the continuous limit I've written here. But this D is there's a more explicit formula, which is a discrete Dirac operator. But its continuum limit and its long-distance behavior really is very well approximated by this. So there's an explicit formula. And the point is that this enables you to do all kinds of calculations. In other words, it's the analog of Gaussian integration, except that these guys anti-commute, and psi squared equals 0. However, you notice that the integral, this integral can be computed exactly, and if you were doing it in a Gaussian theory, you would get a determinant to the minus 1/2 power. What we get instead is the Pfaffian, which of course is closely related to the determinant. So this fact that this is a Pfaffian when epsilon equals 0 means that we can do virtually all computations almost as if they're Gaussian. There are various sign changes one has to keep track of. And of course, the operator that goes behind, that sits in here, is not a second-order operator as we have in Laplacian or as we have in random walk. It's a first-order operator. And that changes the nature of the critical phenomena. The fact that this is a first-order rather than a second-order operator, as we would have in random walk, for example, which is generated by Brownian motion. Or generated by Heather generator, which is Laplacian. So that's a second. This is the first-order operator, the other one's second. So that's part of the that's one of the main mechanisms that we have. Okay, now I realize my time is perhaps almost gone, but let me mention a couple of other models which are related to cellular automata. I'll just have a few minutes to say something about this. So this is there are more conjectures here than there are real theorems, but that makes it, I think, interesting to look at. I'll put everything up at once since my time is running out. This last 2 transparencies are really to try to explain how things like Ising models may be related, presumably are related, to dynamical problems. And they're very simple dynamical problems to state and understand. This is what's called majority vote and noise. Here we have spins which have a time dependence in addition, and we have a discrete time. So the spin at time t plus 1 is related to the spin at time t. And what it does is to figure out what it's going to do at time t plus 1, it looks to itself and its 4 nearest neighbors and looks at what they have to say. If you are plus and your 4 nearest neighbors are minus, then according to this rule, you would flip to minus. If you're plus and you have 2 other neighbors who are also plus, then you will remain plus. And this happens with probability 1 minus delta. And then, so you're voting according to yourself and your 4 nearest neighbor majority. And then, so you do this with probability 1 minus delta. This would be completely deterministic if delta were 0. And then now once in a while you make an error. You even haven't counted right or something. And you get this, and you just put plus and minus 1 randomly. Okay? And you do this, you update sequentially, all these probabilities are independent, and you try to understand, you start, let's say, with all pluses to begin with, and you try to understand what happens with noise. And what's maybe a little surprising is that if you do this in 1 dimension, there's a unique invariant measure, which means what? It means that if I started with all pluses, or I started with all minuses, and I look at the thing for very, very long times, I will not know which data I started with. The noise takes over the system.
No matter how small.
No matter how small. Okay? Unless it's 0. Then of course you remember everything. And if you start with pluses, you will remain plus forever. And you start with minuses, you will remain minus forever. But the minute you introduce the noise, it will destroy your memory of what the initial data was. And that is reflected in the fact that there's a unique mixing invariant measure for all delta positive. Okay?
GAC is a person?
Yes. GAC is a person. CA is cellular automata. Okay? So this is the D equals 1 result for the majority vote. Now, if I have a noisy cellular automata, and I can make the rules as I like, if I have a freedom to make the rules, but my rules should not be very long range, should be short range rules and translation invariant, then rather surprising things can happen which are quite different from this. Peter Gotch at Boston claims, and it's a very difficult proof, that he can find noisy cellular automata, in other words, put the noise in something like this, for which you have infinitely many, in fact, uncountably many invariant measures. That means that you remember your initial data.
Coming back to G1, you allow obviously cellular automata of this particular one.
The Gotch, oh no, this is particular for this particular.
Not known for general.
It's not known for general.
No, it's known to be false. There is a somebody here who knows that I should prove it.
It's certainly not true in general.
But equal 1 is not counterexamples, very subtle counterexamples. But equal 1, yeah, it's not true in general.
Yeah, it's not true in general.
Probably they have integrable cellular automata. They are linguistic.
Well, integrable would mean, and these problems would mean that you have an invariant measure which you understand exactly, and there are such things, certainly. There are such things. Yeah. So now let me go to 2 dimensions. 2 dimensions. Where's it? Oh, 2 dimensions over here. I already have it on the screen. For delta small, the conjecture there are 2 invariant measures. This is still not known as far as I know, except in very special cases of specially adapted noise. So that depends upon the initial conditions. You get 2 invariant measures which are sensitive to your initial condition. All pluses remain plus, all minuses remain minus. This seems like an obvious fact. It's not, unfortunately, obvious. I thought it would be easy to prove. I spent a few days thinking about it, and people have spent a lot longer than I have. And it's apparently a difficult problem, although it's intuitively clear that it happens. It's certainly true numerically. Now, here's the conjecture that brings us back to Ising. That at the critical, see, there's a critical noise. If your noise is very strong, everything becomes disordered. If your noise is weak, then of course you should have some kind of order. And the conjecture here is that at the critical noise, there's a unique measure, which is basically like the two-dimensional icing model at the critical temperature. And the general problem that we would, that is very difficult in general, but I put it up here because it is, I believe, a very important problem in statistical mechanics, to understand properties of the invariant measures for stochastic PDEs, which this is a very baby model for. There are models like Kadar-Parisi-Zhang, and to what extent there is universality. Like, well, here I'm asserting there's some universality, that you get back icing at TC. These are just conjectures, but I think these problems with dynamics are one of the more interesting ones that are wide open in statistical mechanics. And part of the reason is because we don't have the measure in our hand. We don't have it explicitly. It's only determined implicitly by the dynamics and the noise. So I will stop there.